Hello and welcome to another video on Year 12 Maths. So what's going to happen today is we're going to start the course proper. So we've had chapter 0.1 and 0.2. That was part of chapter 1 in the book, but now we're going to consider this as, right, let's get down to business. Let's go from GCSE onto A-level properly. So we're going to have a look at indices and surds. So because I've said we're getting onto A-level properly, it's not to say this isn't going to overlap with the GCSE in any way. Of course it will. You've seen indices and surds before. But what we'll get on to here is just showing and laying the foundations of how they're going to be used later in the course, and we're going to see links as well to the importance of them for A-level in Year 12 and indeed Year 13. So hopefully you know by now there is always a warm-up section of every lesson. So if you have a look at these questions for me, so there's 4 to have a go at. There almost always is 4, by the way. Have a go at the questions first, only play the video and see what the solutions are after you've attempted them to the best of your ability. That's the best way you'll learn from them. Don't just copy down the solutions, that's pretty silly. So once you're ready, press play and I'll talk you through these answers. So let's have a look at the solutions to question 1. So for question 1, we're just told we need to write down the following products in the form 2 to the power n, where n is a natural number, where n is a whole number, a counting number. So 2 multiplied by 2 multiplied by 2, I'm sure you know that's 2 to the power 3, 2 cubed. Whereas part B, 2 times 2 times 2 times 2 times 2, I won't give you any prizes for understanding that's 2 to the power 5. Part C, find the product of part A and part B in index form such that 2 multiplied to the power A times 2 to the power B equals 2 to the power C, where A, B and C are natural numbers. So that fairly obviously is just writing this as 2 cubed times 2 squared equals 2 to the power 5. So as you will have seen from GCSE, have a look at the exponents, have a look at the powers. How do 3, 2 and 5 relate to each other? Well, 3 plus 2 equals 5. This is one of the laws of indices we're going to work on today and also prove. So for part D, write down any pair of natural numbers p and q such that 2 to the power p times 2 to the power q is 2 to the power 5. As you can see here, all we need to do is make sure that these two numbers sum to this final number here. So p and q, we could have 1 and 4, 2, 3, 3 or 2, whatever. So I'm just going to go for, I don't know, maybe just 2 and 3. So I'm going to pick P to be 2 and Q to be 3. You could have picked 1 and 4. That would have been fine as well. So it doesn't really matter. Part 2, question 2. Simplify this fraction here. Well, we can obviously cancel out some of these 3's on the top and bottom. So if we cancel that 3 here, that 3 there, and this 3. So how many 3's are we left with? 1, 2, 3, 4. And so that's going to be 3 to the power 4. But before we move on, just let's think about what this fraction was initially. So before we started cancelling, how many 3's did we have on the top? On the top, you can hopefully see if you count them, there were 7 3's. So it was 3 to the power 7 on top, and we divided that by 3 to the power 3 on the bottom. And so we ended up with 3 to the power 4. Again, ask yourself the obvious question, how does 7 and 3 relate to 4? Well, using the laws of indices from GCSE, obviously 7 take away 3 is 4, and that's how we arrive at the final power of 3. When we divide with the same base number, we simply subtract the powers. So part B, write down any pair of natural numbers x and y such that 3 to the power x divided by 3 to the power y equals 3 squared. There are literally infinite solutions to this, as long as x minus y equals 2. So I'm going to go for 3 to the power 100 divided by 3 to the power 98, because 100 minus 98 gives us 2. As I've said, there's literally hundreds of examples, infinite examples, which would work for this. So if you've not got 198, I'm not entirely surprised. Whatever you've got, I'm sure it works. For example, 6 and 4 would be fine. You get the idea, hopefully. Warm-up question 3. So using the ideas we've used in question 1 and question 2, let's prove this following statement below that it's true. This is almost so obvious, in a sense it's almost hard to prove it as such, it's just almost so obviously true. But using what we've done and just taking it step by step, let's just take 2 cubed squared separately to 2 squared cubed. So if we just think of this one for the time being, and we can sort of think of it on 2 separate sides, then we can compare afterwards. So 2 cubed squared, that just means 2 cubed multiplied by itself twice. 2 cubed times 2 cubed. And then from question 1, we've established that the idea, when we multiply with the bases the same, we just add the exponents, we add the powers. So 3 plus 3, that's going to be 2 to the power 6. So we've proven that this yellow thingy here, whoops, wrong colour, silly me. Go away. There we go. It's 2 to the power 6. Whereas this one here, 2 squared cubed, we're going to use the same idea. We start on the outside of the brackets and work our way in. So whatever is on the inside, we cube it. So we're multiplying this on the inside by itself 3 times. So that's just 2 squared multiplied by 2 squared multiplied by 2 squared, which is the same as 2 to the power of 2 plus 2 plus 2, which of course obviously is just 2 to the power 6. And what do we see here? Well, we see, get rid of that this one is exactly the same as that one. But we started off with them being 2 cubed squared and 2 squared cubed. So based on what we have over here, we can then make the final conclusion that therefore 2 cubed squared must have been the same as 2 squared cubed all along. And we're done. Question 4, we've got 2 different statements, A and B, only one of which is true. So which one is true? Not only that though, we can't just circle the right one, we need to justify the answer and explain why it is the case, why it's true. So what I would suggest is to start with the left-hand side and manipulate it to the correct simplified version of itself. And so what we do here is we start with x to the power 5 plus x squared all over x squared. Now, we're basically dividing the top by the bottom. Each base is x, and so when we're dividing powers of x, we simply subtract the first power. So we subtract the second power away from the first. And so this one here, the x to the power 5, is going to become x to the power of 5 minus 2. And the x squared is going to become x squared minus 2. And so what we're going to have here is x cubed plus x to the 0, which is x cubed plus 1, of course, because anything to the power 0 is going to be 1, but we're going to show you that in this lesson. And so which one of these is the same as this one? Well, obviously you can see that the only one which is the same as the correct one is part A. Part B is completely wrong. The mistake they've made in part B is we've done x to the power 5 plus x to the power 2, it must be x to the power 7, and then done power 7 minus power 2 to get power 5. So this one is completely wrong. This one here is obviously correct, and so it's part A we need to be circling. So let's have a look at the main bit of this lesson properly, the laws of indices. So there's a bit of history to this, which I'm just going to run through with you now. So to start off with, just think about 2 to the power 4, for example. So the shorthand definition of 2 to the power 4 is replaced instead of writing down 2 multiplied by 2 multiplied by 2 multiplied by 2, which takes longer to say and it's more ink to write with. It was first used by Descartes in 1637, and it leads into the laws of indices, which we can now think about deriving by simply counting the number of terms. Before I go on, I did mention about the amount of ink it takes to write down indices in their long form. This was another important economic driving force for the laws of indices coming to the fore and being standardized and pushed. So Descartes was a brilliant mathematician, but one person on their own wanting the laws of indices to be written in a certain way wasn't enough. Often in life, as you'll find as you grow older, often a driving force is about money. The printing press weren't a fan of writing down indices and powers longhand. So indices are obviously a great time saver, secondly a great space saver, and importantly for the printing press, a great ink saver as well. And so not only are indices nice to manipulate from an algebraic and numerical point of view, you can see patterns of them much easier, but also it saved the printing press loads of ink. So it was really a great invention for all concerned, this notation, and the printing press were very happy to go along with it and publish these mathematical books. So that's a bit of history for you there. So just carrying on this bit here. So 2 to the power 4 is what we had. So looking at 2 to the power 4, the number 2 appears 4 times in the product, which tells us that the index, which is another word for the power, which in itself is another word for exponent, must be 4. 2 to the power 4, because we're multiplying 2 by itself 4 times. However, if you have a product containing 150 terms, as I've sort of said earlier now, counting is not very efficient, so you need a better method for it. So let's go forward and have a look at a few ideas. So first of all, to be clear in our thinking, we must consider that what we mean when we write down the number 2, it's not part of a longer product, such as 2 multiplied by 2, or 2 multiplied by 2 multiplied by 2 multiplied by 2, but it's a basic component of any product of any power of 2 and must contribute to the value of the index. So 2 doesn't need to be 2 to the power 4, it can be written as 2 to the power 1, which is just 2, 2 to the power 5, or 2 to the power a million. Doesn't really matter. But what I mentioned earlier, indices do allow you to see patterns much clearer. Let's have a look at this particular following pattern. So 2 to the power 4, 2 times 2 times 2 times 2. 2 cubed, 2 times 2 times 2. 2 times 2 is 2 squared. 2 on its own is just 2 to the power 1. We could carry this on to go to 2 to the power 0, which I'm going to show you in a couple of ways. In fact, I'm just going to quickly mention this now. If we think about these solutions here, 2 to the power 4, 2 times 2 times 2 times 2, that's 16, isn't it? 2 cubed, 2 times 2 times 2 is 8, 2 times 2 is 4, 2 is quite obviously 2. So what's happening each time this power reduces by 1? 16, 8, 4, 2. These numbers are halving, aren't they? So if you just carry on the pattern, half of 16 is 8, half of 8 is 4, half of 4 is 2, half of 2 is 1. And so intuitively, if we carry on the pattern with this exponent, 4, 3, 2, 1, 0, we would expect 2 to the power 0 to be 1. I'm going to try and convince you of that in a different way later on, by the way. Let's move on. So what I'm saying here is, when we see a product such as 2 multiplied by 2 multiplied by 2, we can think of it in separate exponents. For example, 2 to the power 1 multiplied by 2 to the power 1 multiplied by 2 to the power 1, which is the same as 2 cubed. So we arrive at 2 cubed by essentially adding the indices in the product. So hopefully, as you can see here, 1 plus 1 plus 1 gives us 3. So, bit of a warm-up. Obviously now, how can we express 2 times 2 times 2 times 3 times 3 in index form? Well, 2 times 2 times 2 is 2 cubed. 3 times 3 is 3 squared. Let's think about this in a bit more depth. Now we've talked about the language of the laws of indices, we can now be in a position to actually derive and prove them. But before we begin, I'm going to just define 2 distinct natural numbers in index form. So we've got a to the power m and a to the power n, where the base a is a natural number, a counting number, and n and m are both natural numbers themselves. But importantly here, I'm going to define that m is greater than n. So let's start with just thinking about what a to the power m means. That means a multiplied by a multiplied by a, again and again, m times. M lots of a, all in a line, all being multiplied by themselves. Similarly for a to the power n lots of a multiplied by themselves. So let's think about deriving what I've called law 1, which is a to the power m multiplied by a to the power n equals a to the power of m plus n. You should have seen this and be familiar with it already in GCSE in terms of using it, but let's see if we can prove it. So if you think of a to the power m first of all, we will just start off by thinking of a to the power m as we've wrote it earlier. So I've not done anything here apart from just rewrote a to the power m as its definition. In pretty much the same way, if we just do the same for a to the power n, and just in red, we think this n red a's and m blue a's. Just colour coding it to make it slightly simpler to see. So now what we can do is we can think about combining these in some sense. So if we now think that a to the power m plus n, what that's going to be is a times a times a, all these blue a's, multiplied by all these red a's in a line. If we multiply these together and those together, we're going to have m plus n lots of a, which by the definition of a power is a to the power of m plus n, because it's m plus n lots of a in a line multiplied together. And so that's just the same as saying it's a to the power m, which is all of this here, multiplied by a to the power n, which are all these red a's on the right. So we've proven that this bit here is the same as this bit here. In other words, a to the power m multiplied by a to the power n is the same as a to the power of m plus n. Second law. So again, we're going to set it off in the same way and just write down a to the power m. So a to the power m, let's just think of it in terms like this actually. So if you think of it as a fraction, first of all, so any division could be thought of as a fraction. So a to the power m divided by a to the power n, think of it as a to the power m on the numerator, and the denominator is a to the power n. So this is a times a times a, all in blue. This is m a's in a line. Okay, m lots of a multiplied together. And the denominator here, that's going to be n lots of a multiplied together. But now just let's remind ourselves of what we said about m and n. What we said is that m is bigger than n. This is going to be very important to our proof. So in a thought bubble there, I'll just put to remind ourselves of how m and n relate. And so as we know from basic fractions, we can cancel the same terms on the top and the bottom. So let's do this down here. And so we could cancel off a certain number of a's on the top and the bottom. Let's just say I'm going to cancel these. I'm going to colour code what I've cancelled off in yellow. Okay, so because m is bigger than n, what that means is there's more a's on top than there is a's on the bottom. So there's going to be some a's left on the top. Now here happens to be 3, but generally that could be any number of a's. It's arbitrary. There's just going to be some a's left. So what I've cancelled here is all of the n a's on the bottom with n a's on the top. So just to write that down, I'm just going to say there's n lots of a cancelled on the top and bottom. So there used to be m a's on top, but we've now cancelled n of those off. Because m is bigger than n, there's going to be some a's left. So if we had m on the top originally, and n have been removed, it stands to reason that there's going to be m minus n lots of A remaining. In the numerator, and the denominator just cancelled itself down to 1. So what we've proven here is that a to the power m divided by a to the power n, we've cancelled off n a's, and so we're going to have some a's remaining, and these number of a's remaining are m minus n amount of remaining. So we pretty much proved it. That's how many a's are going to be left. M minus n lots of A. So to visualize it, we had m lots on top, n lots on the bottom. Some of these cancelled, and so all of the n cancelled on the bottom. So of these m on top, we cancelled n of them. And all that's left of the original m a's on top is now m minus n lots of A, all multiplied by themselves. In other words, a to the power m minus n. And so that's the second law completed. Before we move on to the third law, I just want to quickly consider what I mentioned earlier about proving that any number to the power 0 equals 1. So let's just think about the special case here. If we just let m equal n for a second. So based on what we just proved here, a to the power m divided by a to the power n equals a to the power of m minus n. So let's just write this down in a different way. So a to the power m divided by a to the power m. For example, just letting this m equal n. Okay, so in fact I'll call this n. So that's going to be equal to 1, isn't it? Because you think about it, any number, any natural number divided by itself always equals 1. 2 divided by 2, a million divided by a million, whatever, that's just obviously equal to each other. But a to the power of m minus n, that's going to be the same as a to the power of m minus m, because n is the same as m, and that's the same as a to the power 0. So we've proven that this thing here, a to the power m divided by a to the power n, is the same as this thing over here. And so therefore, if this here is equal to 1, it's also equal to a to the power 0. In other words, for any natural number a to the power 0 must be equal to 1, because you're dividing something by itself and getting 1, but by the laws of division of powers, we end up with power 0. So in other words, a to the power of 0 will always equal 1. The third law, power of a power, this may have been explained to you. I was taught it as it's the power of a power, so we multiply the powers. So a to the power m to the power n is a to the power of mn. So let's see if we can illustrate this in a more intuitive way. And so first of all, I'm just going to write down a to the power m to the power n as a to the power n m times a to the power m. So there's basically n lots of a to the power m. Okay, I'm just color coded in here yellow the a to the power m. So next, let's just think about what a to the power m means by using this definition here. Each one of these a to the power m's is a times a times a m times. So let's write this out in the longer way. So that's m lots of a, this is m lots of a, m lots of a, m lots of a, with an indefinite number of m lots of a in between as well. So let's just build this up step by step. So like I said, this is m lots, m lots, m lots, and m lots. Now let's build it up in terms of a cumulative total of how many a's we have. So just thinking of this first grouping here, that's just one lot of m. That's the first lot of m, so it's m lots of a multiplied together. But this m lots plus this m lots, m plus m, we then have 2m lots of a multiplied together. This lot plus this lot plus this lot. By the third lot we'd have 3m, then 4m, then 5m, and so on, until eventually we get to the end of the whole thing, and we'd have m times n, lots of a, all multiplied together. N times n is obviously mn, lots of a multiplied together. And so that's the same as a to the power of m times n, but because in algebra we don't need the multiplication sign, that's the same as a to the power mn, which is what we wanted to prove. So a to the power m to the power n is the same as this. So let's try and apply these ideas with a few worked examples now. So use and apply the laws of indices where m and n are natural numbers and m is greater than n. So here we've got a few to try, 4, a, b, c and d. Simplify them down. So part 1, a, 2x5 multiplied by 3x7. Treat the numbers first. Treat the coefficients first. So we have 2 times 3, that's going to be 6. x5 times x7, we just add the exponents. 5 plus 7, that's x to the power 12. So for part B, treat the numbers first. So 12 divided by 4 is 3. A to the 6 divided by a to the cubed, that's going to be a to the power of 6 minus 3, which is a to the power 3. Part C, this is 2b all cubed. 2b all cubed means we're going to cube the 2, which is 8, and also cube the b. So 2b all cubed is 2 cubed, which is 8, and b cubed, which is this. And so all I've done here is I've just changed this bit into that bit. I've left the 4b squared on its own, but now what we can do in the second step is to combine and simplify. So 8 multiplied by 4 is 32, b cubed times b squared is b to the power 5. Part D, 3y to the power 4 cubed, we're going to just cube all of this on the inside. So 3 cubed is 27. Y to the power 4 to the power 3, that's power of a power. So we multiply the exponents. So 4 times 3 is y to the power 12. So I've left everything else on its own. Then times by 2y squared, all over y to the power 5. So let's simplify this numerator. So take the numbers. 27 times 2 is 54. Y to the power 12 multiplied by y to the power 2 is y to the power 14. All of this divided by y to the power 5. So now we can use the subtraction law of powers of indices. Y to the 14 divided by y to the 5 is y to the 14 minus 5, which is going to be y to the 9. So this becomes 54 y to the 9. Worked example set 2. We've got another 2 things to simplify here. And so first of all, part A, we're going to treat these 2 terms in the numerator separately and divide them by the denominator. So first of all, 12x7 divided by 3x squared. 12 divided by 3 gives us 4. x7 divided by x squared is x to the power 5. In the same way, we do the same with this second term. 6 divided by 3 gives us 2. X cubed divided by x squared, that's going to become x to the power 3 minus 2, which is x to the power of 1. Because it's a power 1, we don't need to actually write the 1. We just leave it there as it is. For part B, let's square this first term here. So 5r to the 6 all squared. Well, 5 squared is 25. r6 all squared, power of a power, so multiply the 6 and the 2, we get r to the power 12. Then minus r to the power 7 like we had before. Then all divided by 4r cubed. This can be simplified down slightly. 25 divided by 4, I'm just going to leave this as 25 over 4. The new power of r will be 12 minus 3, which will be r to the 9. Then we can minus off a quarter, because we're dividing by 4 on the bottom. R to the 7 divided by r to the 3. 7 minus 3, that's going to give us r to the power 4. So that's absolutely fine. If you wanted to, you could slightly improve on this if you wanted to. There's a common factor of a quarter. So you could say, if you wanted, it's the same as a quarter of 25r to the 9 minus r to the power 4. Okay, and then we're done. So now it's over to you. So as ever, what you need to do is practice these skills yourselves. What I want you to have a look at is page 3 in the main algebra book, exercise 1A. Try these parts of the questions. So check your answers on the back. If you're stuck, ask me, either in class, on an email or the comments section, and don't suffer in silence. If you finish those questions, ask me for what else you can do afterwards. Don't just sit there twiddling your thumbs. So work hard, complete all these, and make sure they're all correct. So thanks for listening. You'll hear from me again in the next video, and I'll hopefully see you soon. Thank you.